bookkeeping which will be done, and that bookkeeping is done with the help of this structure variable. So what will happen? A structure variable will be created. So this structure, as we discussed, it is called a task structure in Linux operating system. Now what all should this structure have? That is what we were discussing. So can you give me a few pointers about what all things do you think that we should bookkeep about a process? So we have taken a look at the process life cycle. This is how a process life cycle is, and your job as a system software engineer now is you have to create this structure and you have to decide which all variables should be a part of this structure. So what all fields would you want? So look at it, your process, it is moving between all these states. Sometimes it's in ready, sometimes it goes to CPU, it comes to a running state, then it comes to the waiting state when it requires an input output. It is moving here and there. So what all would you want to bookkeep? You can also see it like students moving around in an institute. They come in the first year, they go back in the fourth year, and between this first and fourth year, they do a plethora of things. It might be academics, extracurricular activities, placements, projects. There are so many things. Same is the case here with processes. From the time they come in this system and before the time they go out, they are doing multiple things here. So what all would you want to maintain about a process? So all the things which are changing about a process, we should maintain them. We should do a bookkeeping for them. So what all should be a part of this bookkeeping is the question. And we have discussed that we are going to have one thing which is ID. So every process which comes in the system, we are going to give it a process ID. And we have seen the process ID of various processes on a Windows system. The ID is just for identification. What else? If you look at this figure, yes, go ahead.
The state of the process.
The state of the process, very good. So the state of a process, it is continuously changing. It can be ready, running, waiting. So system engineer, he should know what is the state of a process, or your kernel should know what is the state of a process, right? Because if the state is ready, I have to look that the state is ready, and then that process, it should be one of the candidates to be chosen by the CPU so that I can run it on the CPU. Okay, ID state, what else? A very important point which we discussed yesterday.
Priority.
Okay, priority. Definitely, I can have a priority for each process. I should maintain that. The processes which have a higher priority, they should run before others who have a low priority. Okay. What else changes when a process executes?
Data in it.
Data in it, very good. So this was what we discussed yesterday. So the data changes, right? I should maintain that. So I should know. The most important thing here in the data, I can say it can be the instruction number or the instruction pointer.
Instruction number, yeah.
Right? I should maintain that first of all. So I should know that the process has run till line number 15 or it has run till line number 16, and I'm going to pick it up from there. Other than the instruction number, all the previous data which it has computed, what we were discussing yesterday, that should be stored. Right? So that should also be a part of this data structure. Okay. Other than that, is there something else? Sometimes processes, they might use some file. So you might have opened a file. You might be doing something with this file. Maybe you are reading, you have written, let's say a Python program or a C program which reads a file, opens it line by line. Maybe it's counting the number of characters or the number of lines. Maybe you are done till the 71th line, but the file has like 1000 lines and the process is switched. So I should also note which files are opened in the system for this corresponding process, which files this process can use. We will talk more about that in another unit on file management. So these all are the things which have to be stored in this data structure. process state. So some of the things which are very important are process state, process number, which is also the PID, and program counter registers. These are other some miscellaneous data. So all these bookkeeping should be done, a list of open files and stuff. Now, if you look at it, you can represent it in the form of a code as something like this. This is how a task struct looks like in a Linux system. This is a special variable. It's not an integer variable. It's a variable of type PID. Maybe it can be another structure as well, or it can be a class. So it's a process identifier. Then state of the process. These three things are really important, right? PID, state of the process, and at the end is the address space of this process. So we just now said that we are going to store the state of the process in terms of where was the instruction register pointing and what was the state of all the other CPU registers when this process was executing. So we can keep note of that data using two ways. Either I can keep all that data here in the form of registers and different variables. But a better way to do that is, yesterday we discussed that when we map a process in memory, so there is a separate register part for it, right, where it maintains all the registers, and then there is some heap and stack which have all the other variables. So instead of having the values of all these variables separately in that structure, we can maintain a pointer which actually points to the memory location of this particular process, and we can get the details from there. It's a smarter way of doing that. And we can have priority, definitely. Other than priority, we can have a time slice. It is used when you in the scheduling. So we will talk about it soon. So time slice is something like, I might say every process should run for 10 milliseconds and then it should switch with another process. There is where time slice come in. And then we have two more fields here, which are parent and children. We are again going to talk about it soon. We have said that there is a different way of creating a process in the system. So there can be user processes, system processes, background processes, or daemons. We also can have a process which is created by another process. So that's what we talk about. A process can also create another process. In that case, a process, it has to keep a track of which is its parent process and which who all are its child processes. So we'll talk about it in a while. So these are some things which should be a part of this task structure. Now coming back here. Am I audible? There is a power outage. Just give me a second. Am I audible?
Yes,
Just give me a second. I have to rejoin this meeting from my iPad. Okay, so here we were. So we were saying the moment a process is created, your operating system or your kernel should have another process running, which should create a process control block for the process we just clicked on. So let's say it's my new process. It was a program, and as soon as you clicked on this program, it became a process in the form of a process control block. So we call, or a task structure. So both the things mean the same. And now, who does the work of creating this process control block? It is some other process which is being run by the kernel or the operating system, and then that process should also be somewhere in memory, and that process should also be having a process control block of its own. So it's like a chain. If I see my memory here, There is actually one process which is already sitting here. So it can be the kernel process. Some process of the kernel is a bunch of processes, and then when a new process is created, this process creates a process control block for this new program or for this new process. So there is a bit of technicality here which we should understand. So generally what we do, we divide our memory in two parts. One is called the kernel space, kernel address space, and one is called the user address space. So all the programs which your system is running, all the system programs, they reside in this kernel space. And whatever you are going to run, all those programs, all those processes, they are going to be mapped here. So the reason for that is any process which is running in the user address space or any process which is created by the user, it is not allowed to actually go and peep into the address space of kernel. So you can always in and out look around the memory which belongs to the user address space. Even for some other processes which are running in the user address space, but you cannot access something which is in the kernel address space. And that is the reason we get segmentation faults sometimes, because we are trying to access that memory location or write something which belongs to the kernel space. So the program crashes. And now you might be wondering, so you can't even access these particular addresses which belong to this part of your memory, which belong to kernel. And then you can say, isn't it like I can access each of my memory locations? So I can just write a counter if I know what will be the maximum hexadecimal number I can use to represent my memory. I can always generate numbers like 0, 1, 2, 3, 4 up to FFFFF. Let's say this is the maximum possible address in my system and access each and every memory location. But the answer is no. So things do not work out really this way. We will talk about it more in the memory management chapter. So the idea is you can never access anything which is in the kernel address space. A user program is not allowed to do that. We can always look at your address space. So if it's a kernel process, it will be residing here in the memory. If it's a user process, it will be residing here. Now the question is, where should be this process control block for a user program? I'm running a C program, so I clicked on the executable file and we just said that a structure is created. A structure variable is created. So this structure variable should also reside somewhere in the memory. Where should it be? What do you think? Should it be in the user space or should it be in the kernel space? And also, please note that this structure variable, this PCB which we created is very different from what we discussed before. Process in the memory. Process in the memory is still here. It has all that text, data, heap sections, everything is here corresponding to that executable file. This structure, it is a different thing. So it is a data structure created by your kernel so that the kernel can do all the bookkeeping. So where should this process control block lie? Should it be in the user space or should it be in the kernel space? So please note that anything which is in the user space, it is susceptible to accidental damage. Anything which is in kernel space, a user cannot touch that. So where should a process control block be? Should it be in the user space or should it be in the kernel space?
The kernel space.
It should be in the kernel space, right? Because if it is in the user space, then maybe a user can write a malicious program and he can change the states of other processes, or maybe he'll change the priority of other processes as we discussed. He will be able to touch all these data structures which are created. So generally these PCB, they lie in the kernel space. And then it brings us to another technicality. In what form will they lie in the kernel space? Will they be just hanging around like different structure variables? How will they exactly be maintained? So what happens is, so previously when we talked about a process in memory, so you remember stack is a part of process in memory. So process in memory, it had stack, heap, text, data and registers. So the stack part, why were we using the stack part for a process? For function calls, right? When the flow of execution changes, we require that stack. So there are actually two types of stacks which are created. As of now, we just said stack, we didn't go in detail, but this stack, there are two kinds of stack which are created. One is the user stack and other is the kernel stack. So it happens for every process. So every process has one user stack and one kernel stack. User stack, it resides in the user address space, and kernel stack resides in the kernel address space. So you cannot touch anything which is there in the kernel address space. Only the system programs can touch whatever is in the kernel stack. Whatever is in the user stack, you can touch that. So this process control block, it is actually placed as the first thing in the kernel stack of the process. So here you will be having the PCB for that corresponding process. Kernel stack is also used for other things. It's not just for the process control block, but more things. So maybe you are issuing some system calls. Those system calls, they will be using the processes which are in the kernel space, and then one process might be calling the other. There you might need some stack. So for all that information, a kernel stack is used. So there are parts of your program, there are some parts of your program which doesn't require access to any hardware. There are parts of your program which require access to hardware. So anything which requires access to hardware or resources, that run in the kernel address space, and remaining things, they run in the user address space. So now we are clear about process control block. And where it sits, what is it? It's a simple structure variable. Now, how do we use it? So to understand that, I would like to show you this another view of the life. So we have already looked at the life cycle of a process. Here we were talking about a single process, how the single process changes its states. So to the operating system, things will look something like this. So ready queue is nothing but all the processes which are sitting in your memory. So there are a lot of processes which are sitting in the memory waiting to be executed. What operating system does is it maintains a queue of those processes. And what is this queue going to be? It's actually a queue data structure itself. So every process, I'm representing it as a structure variable, which is the process control block. This queue here, it is a linked list of all those structure variables. So PCB1, it's, let's say, the structure variable for the first process. It will be pointing to the PCB2, which will be pointing to PCB3, so on and so forth. So you can maintain this queue as a linked list. As you know, we can even implement priority queues using linked list. So this ready queue is nothing but a data structure which is maintained by your operating system, which is in the form of a linked list. And then you have some scheduling algorithms here, which we will discuss soon. These algorithms, they will decide which of these processes should be executed and will allocate it the CPU. Then when a CPU is running, when a process is running, so we discussed exactly one process can run at a time. It will either execute all the instructions and get terminated, or one of these things will happen, as we again discussed before. So it can go for an input output request. So it might be a scanf statement, might be a printf statement. In that case, we have discussed that the process goes to the waiting state here, right? And it waits for that input output device. So this waiting state, it is represented here in this diagram. So you see what is happening with these processes here. Here is another queue, because input output devices are also mostly only one in the system. CPU is also only one in the system, and the processes, they have to share these resources. So maybe when a process comes for the input output request, there is another process which is already using the input output. So let's say I have run multiple C programs, all of which have these scanf statements. So till I do not serve the terminal or I do not give the value to one process, other will be waiting. So input output devices also maintain a queue, which is just like the ready queue. Rather, each device has its own queue where processes, they are queued up and they are waiting for that particular device. So this input output queue, it can also be represented again as a linked list of the processes. It is another queue of the processes. Other than input output queue, the time slice of the process might be expired. So what does this represent in Where is this in this diagram? So we have seen that many a times when the process is running, we can forcefully fetch the CPU from this process and give it to another process, because a process should not run for too long. So there is when an interrupt comes, or we say the time slice of this process has expired, let's give the CPU to some other process. So that is here. So either your time slice can expire. If the time slice expires, you again go back to the ready queue, or fork a child. We will talk more about it soon. Fork a child here means that this process might create another process. So if a process creates another process, what happens is the process waits till its child executes, and the process resumes its execution after the child has finished processing. Something like that. And we will talk more about it. So this is another thing which can happen, or some other kind of interrupt might occur in the system. So it might be waiting for an interrupt, and when that interrupt occurs, you can again go back to the ready queue. So these are some things which happen with the processes and how they run in the system. Now, in order to get this system running, we actually require some kind of schedulers. And schedulers means basically which process to select from here, from the ready queue. That is the most important scheduler which is needed in my system. So this is another view of the same process again. So here is my ready queue. Here is my input, output or device queue. So there are three kind of schedulers which we use. The first and the foremost most important scheduler is the one which is sitting here between the ready queue and the CPU, which is going to select one process and feed it to the CPU. We call it a short-term scheduler. Can you guess why we call it a short-term scheduler? What can short-term mean here? Why is it short-term? What does short-term means? So short term here means it has to execute very frequently. It doesn't get a whole lot of time between two subsequent runs. So as we discussed, you will not allow a process to run more than a few milliseconds. So you see, after every few milliseconds, the scheduler has to select a process from the ready queue. So it is executing like every few milliseconds in your system very frequently. That's why we call it a short term scheduler. And you should also realize here, the short-term scheduler, it has to be very fast. You know, if it is even, it becomes slightly slow, the CPU will become so much inefficient, because you see, even for the short-term scheduler, it is nothing but an algorithm which is going to select. It's also a process which is going to select another process from the ready queue and put it to the CPU. So this short-term scheduler to run, it will also require the CPU. So assume that when I'm executing some processes, assume that I execute a process for 9 milliseconds, and then assume that the scheduler, it takes 1 millisecond to actually figure out which should be now the next process and switch it. So for 9 milliseconds a process is running, and then for 1 millisecond the scheduler is running to select a process from the ready queue. You see how much of CPU wastage is happening here. This 1 millisecond of time where you are switching, it's actually an overhead. We are just switching between the processes so that we can provide that multitasking experience to the user. But then this switching should not take too much of CPU's time. Otherwise the CPU will become inefficient. So in this case, out of 10 milliseconds, 1 millisecond is going to the scheduler for switching. It means 10% of the CPU is getting wasted here just for scheduling. So we want to keep this wastage as low as possible. Is someone saying something? Okay, so this is one scheduler about which we will be talking in detail. There are few other schedulers which we should talk about. So there is this scheduler sitting here, long-term scheduler, and it sits somewhere, you can say, near to this new state and the ready state. Right, ready state is here for all the processes who are in the ready queue. This is the place where a process is created. So think about this. Assume that I click on 100 files. I do double click on 100 files. It means that 100 processes are created, and then all those 100 processes will come and sit in the ready queue. So we on our personal computers, we generally do not do that. But previously when there were batch systems, so a lot of processes, they had to be executed together. What will happen if you put a very large, you put a very large number of processes in the ready queue? It means there are a whole lot of processes in your memory. That will also reduce the utilization of your system. The more are the number of processes in your memory, more will be the switching, and CPU will become less efficient. So what this long-term scheduler did, it actually controlled how many processes should be sitting in RAM at a time. So till now we haven't talked about that. We said that whenever you double click a process, it comes into the RAM, but you can also put some restriction there. So at a time, how many processes can be there in the RAM? The long-term scheduler, it looked after that. It is mostly absent in today's system. It is not there in Windows or Linux. Whatever process we double click, it goes in RAM. But for certain kind of system, certain kind of operating system, this scheduler is important. So this scheduler, it has two functions. So first of all, it controls what we say as the degree of multi-programming. Degree of multi-programming means how many programs can you run together. So whatever number of processes are there in RAM, it means you can run that many number of processes together. Together means you can juggle between them so fast, providing a multitasking experience to the user. So long-term scheduler, it controlled how many programs a CPU should juggle between at a time. Another thing which it did was, there are two kinds of processes. So you see there are two kinds of resources which are very important in this system. So one resource is definitely the processor, and the second resource which is very important are the other input output devices. So we can actually divide our processes in two types. One are the kind of processes which requires a whole lot of CPU's time. They are, you can say, calculation oriented programs. They want to use ALU as much as possible. And there can be some other programs which are input output oriented. So if you are writing a machine learning program which is mostly doing some kind of pre-processing on a file, so it is using input output a whole lot. So we call those programs as input output extensive programs. Rather, the formal terms for these two processes is, one kind of processes, we call them the CPU bound processes, and other kind of processes, they are input output bound processes. Right? The long-term scheduler also took care of that. So how it took care of that? So you should not, what it said is, you should not feed all the CPU bound processes at once, because then the processes which require input output, they will all be sitting here in this job pool. They want to be in the ready queue, and these input output devices, they will be relatively idle, because all the processes, they just want CPU. No one requires input output, and neither it should be the opposite way. So you should not keep only the input output processes in memory, because in that case CPU will be idle, because no process wants to do any computation. Every process just wants input output. So one aim of this long-term scheduler is, it should somehow choose a very well-defined balance between the input output bound processes and the CPU bound processes. There is a third kind of scheduler which is very interesting, and it is called the medium term scheduler, something which sits between the short term scheduler and long term scheduler. So can someone tell me what happens when a C program is running, or let's say you are running any other process or program on terminal, and you press a control C?
It stops running.
It stops running, it is killed. It just not only stops running, it is killed. It is brought back from the memory and it goes back to the hardware. Okay, what happens if you press Control Z or Control Z?
It becomes a zombie process.
It becomes a zombie process. Is zombie the exact term for that? So what Ananta means when he says it's a zombie process is, it doesn't get killed. It is still somewhere, but it goes in the background. And then you can bring it back to the foreground. Some of you might have done this. So Control C is different than Control Z. What is actually happening when you press that Control Z and we say that the process, it has become a zombie? as Ananta says? What actually happens? Can you think in terms of, so it is definitely not using the CPU at that time. Where is the process sitting at that time? Is it in the memory? Is it in the ready queue? Where is it? So according to me, every process which is waiting to run should either be in the ready queue or should either be in the input output waiting queue at a time. Is there any other place where a process can be? So that is the work of this medium term scheduler. So what you might want to do sometime, you might realize that there are a lot of processes in RAM, there are a lot of processes in ready queue, which is sort of slowing down my system. So can you temporarily fetch out a process from RAM, put it somewhere else so that you reduce the number of processes in the RAM, which will increase the utilization, CPU utilization, and after some time, can you like push back this process in the RAM? So that is what medium term scheduler does. So even a process, let us say it has executed 50% of it is yet remaining, the process has not yet completed, still requires the CPU. What you can do is you can temporarily fetch this process from RAM, put it on hard disk, not as a program, but as a process. It's with its entire state. So as of now, it is not in the ready queue, so it will not get the CPU because it's not in the RAM. And after some time, you can put it back in the RAM and then it will start executing. So that is the work of medium term scheduler. What I described to you is called swapping. And we will discuss more about it in the memory management unit. So in this unit, our focus of attention will be only the short term scheduler. So these are some kinds of schedulers, and we'll soon be talking about scheduling policies. But before that, I wanted to show you a few things. So this thing of when we say a process can create another process, somewhere here we say, right? A process can create another process. This sounds interesting. So let's explore it. So what I was trying to do is I was trying to execute some commands on my Linux system, but then I realized I don't have MS Teams installed there. It will take some time. So if any of you have a Linux system, can you help me out? I'll just give some instructions to you and you'll have to execute them on your terminal. Is any of you currently sitting on a Linux system?
Could you give me 1 minute? I will share my screen.
Sure. Take your time and share your screen. So whatever we are going to do now, you can also do it on a Windows system, but it is more involved on a Windows system. So you can always Google search for it and replicate these steps on a Windows system, but Linux provides a very easy way of looking at these things. So that's why we are doing it on Linux. So let's look at these processes, how they look in Linux. Can I look at how many processes are there in the system? Can I see which is a child process, which is a parent process? And can I as a user create a process from another process? Let's look at some of these things.
I started sharing my screen.
Yes, just give me a second. Can you run the top command first? Right. So here you can see the processes on this system. So we have done this in yesterday's lab also, but let's do it in a bit more detail today. So you can see a PID for each process here. You can see the user which is running this. So you can see there are two users here. One is Shrikar and other is root. So root is for all the processes which are run by your system. Okay, let's guess what are all the other things. So you see this PR field and the NI field. Can someone guess what PR can stand for? We have talked about it in the lecture.
Is it the priority?
It is the priority, yes. So PR here is the priority And actually here a negative priority means a high priority. So you can see that the root process, it is running at a priority of -51, which means it has a high priority. Ni is another priority parameter which is used by your operating system. It is called something like a nice value. So for now you can just assume that it's also a priority. Then you see this VIRT. VIRT, it stands for virtual memory. And again, we will talk more about it in the memory management chapter. Moving to RES. RES here is a resident memory. So this tells you the exact amount of memory your process is using. So for each of your process, you can see how much of memory it's using. As you can see, I think Teams is using quite a lot of memory. And also this command, no top command, it doesn't show you all the processes. It shows you those processes which are heavily utilizing the CPU. So you can see here, Teams here is utilizing something close to 38%, sometimes 36% of the CPU. And then it's percent memory utilization. Time is nothing, but it tells you from how long is your process running. Not our time, but the CPU time. So for a CPU, how much time it has used from the CPU, how much of CPU's time it has used. So these are a few processes. Okay. So in a Windows system, you can use something which is called a process monitor to look at these things. And now let's look at one more thing. So we are saying that there are processes which create another process. If you guys have read the bootstrapping document, which I asked you to read, booting, can someone tell me what is in it there in booting?
It is the first process which is created, and then all the other
Yes,
processes have gone from that process.
exactly.
Initialize in it.
Yes. So init is the first process which starts running on your system when it gets started, and then init, it gives birth to other processes. So let's say I want to look at which are the child processes and which are the parent processes in my system. So we have a command for that. Anand, can you type that? So it is ps3. Maybe I can type it in the chat window. PS3, and there is a -p there. Okay, so look at this. So if you scroll up, you can realize that, just go to the top of this. Maybe you can even increase the size of the terminal window. Yes. So look at this. So this is a tree, right, which starts from system D1. So as of now, there is no init. So init has a PID of 0. If you look at system D, it has a PID of 1. So it is actually the second process which is running on your system. It is a child of init. And then the system ID, it is creating all these processes, which you can see network manager, account daemon, Bluetooth, and all this. And somewhere if you scroll down, you will be able to see MS Teams, and you can figure out which is the exact process who is the parent of MS Teams. Then there are certain processes for genome. Genome is the process on your Linux which gives rise to the graphical user interface. So you are able to interact everything with the help of cursors with this. Yes. So if you look all these things, right, web content, I think these will be for the web browsers. And if you scroll up, yeah, you can see, so there are so many Firefox processes which are running. So probably Ananta has a browser open.
Yeah, I have a lot of browser windows open.
Can you just go up? Let's realize who is the parent of all these Firefox processes, who is their parent, so on and so forth.
Here we have Firefox.
Right, here you have Firefox, and then go up.
System.
Systemd, right? So it is systemd which has all these Firefox processes. So you can look at these processes like this. What else? Just give me a second. What else I wanted to discuss? Okay, if you want to look at the parent of a particular process, you can use this command. So we are going to use this command soon, PID, right? So you have a PS minus F and you can follow it with the process ID. So it will give you the ID of the parent process of that particular process. Maybe you can run it and show it, Ananda. For any one process, just you randomly pick.
Okay, I'll just take WPS applicant and
Right? And then from here you can backtrack. So if you look at this PPID here, it's the parent process. Right? So for this process 700, it's directly 1, which is your system D. And can you look at what is the parent ID for system D? Basically, what is the parent ID for 1? Right?
this is 0.
It says 0, right? And 0 is what? If you look at on the right side, it is sbin backslash init, right? So, and try to do it for 0. Try to look at what is the parent of 0. Right, so it says that it process ID out of range. So init is the you can say the grandfather of all the parents or grandmother of all the parents on your system. Now what we'll try to do is, how much time we have? We have 10 minutes. So we'll do a very interesting thing. So now let's see, can we create process from a process? So we know that we have seen that our system softwares, they have processes, and those processes, they are giving birth to another process. Now let's find out, can I as a user create a process from another process? And what I mean by that is, we will try to write a C program. So if I look at a C program, when it becomes a process, it is a single flow of execution, right? It should be only one process. But then can I write my program in such way? So I'm going to write a C program, but it will be written in such a way that when you execute this C program and it becomes a process, somewhere while executing, it will give birth to another process. And that another process will also start running in the system. So it's like process is reproducing. Just like human beings. The only difference is, for human beings, you have 2 parents. Here, every process has just 1 parent. So can you just open an editor where we can write a C program? Just give me a second. So we'll need some libraries to do this. I'll tell you what the libraries are. So these are some system libraries which will help us. So can you just include them? Okay, now have a main function and just have a printf hello world. That's it. Okay, so what will be the output of this program when we run it?
It will just print hello world.
It will just print hello world. Now let's do something. So what I want is, when this program runs, I want it to create another program, and that program should also run with it. So I want to create a child of this program, and it's very easy. So what you have to do is, before hello world, just place this statement which is called fork. So many of you would have heard about it before. Now before running, can someone predict what will be the output?
Will it print hello world twice?
It will print hello world twice. Yes, that is correct. I can just execute it and look at it. Okay, so it prints hello world 2 times. So what is happening is, as soon as your compiler, it sees a fork, sorry, when you run this program, so what happens when fork comes, this process, it creates another process, which is the child process, right? And this child process runs side by side with this process. So what happens after this 7th statement, The child process here, you can also call it a clone. So it's an exact replica of the same process, but it will start running after fork. So both parent and child, they will print hello world. Both of them are together running. Okay. What will happen if I have this fork in the 9th line, basically after the printf statement? It means that I'm creating a child after printing the hello world, right? And when will child start executing? Child will start executing the instructions only after that. So can you do that? Let's move fork to the 9th line and then execute this program again. Right. So this hello world, it has come from parent, and after printing the hello world, parent gave gave birth to a child, but the child had nothing to do. So it just executed and got over. This hello world comes from the parent. Okay. Let's try to look at these processes using our terminal. So assume that using my terminal, I want to see which is the parent process, which is the child process. So I need to make a few changes in the code. Let me go back to the C code. So move fork back to the 6th line before printf, and after that put a scanf statement, right? So that are both parent and child at this time. So they will not just quickly run and execute, otherwise I'll not be able to see them on my terminal. So this scanf, it will ensure that both of the programs, they are waiting. They will be waiting in the device queue. Right? They will not be terminated, so that I can sort of see them in the list of my processes. Okay, and do one thing, first you compile this. While running this process, give it a separate name other than /a.out. How do we do that? Exactly. Right, now let's run this process temp. Press and enter. Right, so now these processes, they are waiting for input, but I somehow do not know. So both parent process is running and the child process is running, but I don't know which one is requiring the input here. Let's move this to the background. So just press a Control Z. Right, and now let us try to see which all processes are running. So instead of top, try typing this. So PSU followed by the username, which is, I think, Ananta on your system, right? So PSU will ensure here that you see only the processes which are being run by the user. So can you see the names of both these processes somewhere, which we just ran? Right? So we see it here at the end. So we see process temp and we see two processes running. Names are the same, but their IDs are different. Right? Names are the same because it's the same program running, one for child and one for the parent. But the ID of one is 26033 and other is 26034. You can also look at which is the parent process of 26034 and it will tell you it's 26033. So if you type that command here, ps minus f followed by 26034. Yeah, so this ensures that the parent process of it is 26033, and then you can go back in hierarchy and look at who is the parent of 26033, and ultimately you will track back down to init. Okay, so this was what I wanted to show you. So you can now bring those processes back to the foreground. Just type FG and you can then give inputs to these processes. Right? Okay, now both the processes got over. Now the question is, can someone tell me what is the use of this? If you read any operating system book, it will talk about fork, it will talk about a parent process creating a child process. But why would someone want to do this? Do you see any practical application of this?
For a singular program, if you want to test multiple parameters, we can do that.
Okay, if I want to test a single program for a multiple parameter, then I can just put in a for loop with different parameters and then I can check it, isn't it?
On an operating system level, we will have multiple things running. Not like we can't have everything running in one single piece of code. Like for example, the networking, uh, and so on. We'll have like multiple things. So to handle all that, it will be better if we have one process for each of them.
Okay, that sounds good. So there is probably one process which creates these child processes. Okay, can you as an engineer make use of this in your C programs? Assume that you're writing a very big C program for a machine learning application, or let's say for some data analysis task. Can you make use of this? So one very nice thing about it is, if you see here, so both the child processes and parent processes, they run together, right? So are you able to see that both of these processes, they run parallelly? It is kind of providing you parallel processing. There are other ways of parallel processing. So you can use multi-threading for parallel processing. Some of you might have used it. It's another way of parallel processing, right? So if somehow, so here the problem is both parent and child, they are doing exactly the same thing. Parent is typing hello world, child is also typing hello world, because child is an exact clone of the parent. But if somehow I could make child do another thing from a parent, so let's say there is a C program, it's doing two mega things for you, and these two mega things, they are independent, they are not related in any way. Then there is no point in writing just one program and assume that I want to have them in one program. So they will run sequentially, because C programs run sequentially. But you assume that I want to write a single program which runs both of these things, both of these chunk of codes parallelly, then I can make a use of this. But then I'll have to ensure that parent is doing something else and child is doing something else. And how will I do that? Given that I know that child here is an exact clone of parent. So whatever is written in the program, parent will do also the same thing, child will also do the same thing. So in tomorrow's lecture, we'll have a look at that. How can we make child and the parent do separate things? Okay, any other questions here?
Ma'am, as you said, wouldn't multi-threading be a more realistic and efficient approach than actually creating processes?
That is a good question. So why should I use this slightly complicated looking way when we have multi-threading? So there is a small thing which makes this kind of parent-child relationship better than multi-threading. We will talk about that. We are going to talk about multi-threading after a few lectures. So the reason is, when you do multi-threading, it's the same process, right? So, and same process is having multiple threads. So we know that whatever data process has to use, that process is in the memory. So in multi-threading, what is happening, all these threads, they are using the same data. So let's say there is thread 1 running, thread 2 running, they are using, they are having the same space in memory. So assume that by mistake thread 1, it changes something on that memory, and thread 2 is also working on the same memory. So it can create those kind of troubles here. But if you create a child in this way, what happens is child has its own memory, parent has a separate memory. So although it's a child, it's a clone of the parent process, but both are different processes and both also have different space in memory to keep their data. So assume that I was also having some variable here in this program, int I, int j, and I was making changes on this on that data there. So what will happen, parent will have its own copy of data in the memory, child will have its own copy of data in the memory, their data are separate, right? So that is how multi-threading is different than this. Multi-threading is definitely a very good way to parallel processing. This way is not much used for for parallel processing. Multi-threading is mostly used. But yes, one thing is, you have to be very careful with multi-threading, because all the threads, they are using the same data. And we will talk more about that in inter-process communication and race conditions, when we don't want one thread to change the data of some other thread and things like that. Okay, any other doubts? Okay, then you can leave if you have no doubts. If you have doubts, you can stay back.